We said in the introduction to Module 1 that distributed systems are all around us. We also introduced another kind of system, much larger and with much more diverse functionality, distributed ecosystems. Today, we will discuss definitions of distributed systems and ecosystems and how to differentiate them from other classes of computer systems, in particular from parallel computing systems that appear commonly in high-performance computing. You should be familiar with this overview of how distributed systems and ecosystems support all digital aspects of our modern society. Where are these distributed systems and ecosystems? Well, everywhere the arrows point. Let's start with the light blue, borderless arrows. We already expect that such systems, distributed systems and ecosystems, include hardware devices spread around the globe or even present at some distance in a large room. We also expect they include the networks that allow such devices to interconnect so they can communicate, and the software that allows the same devices to collaborate towards some helpful goal. But there is more, indicated by the orange arrows with the light border. These indicate that, although the applications are used locally by people or other applications, their operation depends on more software and hardware components, operating locally, but that further connect with the rest of the distributed system and ecosystem. These are also parts of distributed systems and ecosystems. Let's see an example. Consider a video conferencing system, a VCS, pronounced VCS, a class of distributed systems very common in the education and business world. VCSs have as their main function to enable groups of people to communicate easily, typically through audio and video feeds, wherever the people may be in the world. Familiar instances include Zoom, WebEx, Microsoft Teams in the commercial category, and Jitsi in the free-to-use open source category. In the future, as our understanding of the metaverse develops and new technologies appear, we expect that the typical video conferencing system will include more communication capabilities, more kinds of feed, etc. A video conferencing system is typically built as a distributed system, with the architecture underlying all systems of the same type depicted in the slide. The system is distributed because the emitter of an audio-video feed, component 1 in the slide, and its receiver, component 9, are physically separated, so information must be communicated between them. This information contains audio, video, and metadata. To ensure performance and other quality of service properties, the distributed system includes a sender and a receiver component, components 2 and 6 respectively in this figure. The sender and the receiver run on the local computers of the people in the video conference, automatically performing their functions. They use typical networking technology to form a connection, components 4 on the different machines, over the internet. Because of how audio and video information is captured and the temporal nature of this information, the sender ensures the information is properly encoded for transmission, component 3, and then that is decoded upon receipt, component 7. The encoders and decoders are highly advanced and efficient and fully automated. It would be rather inefficient and possibly lead to many problems, including performance issues, to have each sender encode and transmit streams to each other receiver, especially as the conference size increases. Instead, the architecture includes a more powerful, centralized component, a data center, which acts as a video conferencing dispatcher, component 5, which manages multiple servers, each of which can manage the conferencing needs of actually many people engaged in possibly different conferences. Sophisticated dispatchers can manage their resources very efficiently, provisioning more servers to scale the VCS service when the number of concurrent people engaged in the video conferencing increases, and releasing idle servers during periods of low need. Only by combining the operation of each of these components can a VCS operate. It is a good moment to generalize this description towards a definition. A distributed system is a group of 2 or more constituents or components, often homogeneous, so performing the same function and operating with the same behavior. The components are physically distributed, so they need a network to communicate. To disambiguate in physical terms, the time it takes for components to communicate with each other is significantly longer, for example, an order of magnitude or more, than it takes components to access information locally. Constituents orchestrate their actions, meaning they work together. Working together can take the form of cooperation, working together towards the same goal, co-opetition, where some of the goals are aligned, for example, a mutual benefit, but whereas other goals may be even competitive in nature, for example, who gets paid, who controls the system, and others. Constituents may be autonomous, meaning in some cases they may take their own key operational decisions, for example, whether to even stay in the system. The system structure and organization ensure the responsibility of the distributed system. This responsibility can be described and includes completing specific functions or services, doing this well, so providing desirable non-functional properties such as high performance, high availability, and low cost, and possibly being subject to a clear contract that is commonly known as a service level agreement, an SLA, comprised of many objectives with associated penalties for the case they are not met. A typical responsibility of a distributed system is to run digital applications that arrive in the system at some point in time, until all these applications are complete, without issue, and with high efficiency. The set of digital applications the system needs to run, combined with their arrival process, where and when the applications are submitted to the system, when and where do requests from users arrive, forms the workload of a distributed system. There is one more complication. Such systems are often dynamic, and distributed systems are highly so. Long and short-term dynamics occur in distributed systems, meaning events occur making the system temporarily unstable. For example, a component may need to be replaced or may fail. In such situations, systems must take decisions to redress towards desirable, possibly stable operation. Long-term dynamics, such as changing a component of the system radically, occur with intervals between such events exceeding greatly those of typical events in the system. A typical rate of replacing components could be every few years or every few months. In contrast, short-term dynamics, such as the unexpected arrival of a large part of the workload, a spike, occur at the rate of typical events in the system, such as minutes to seconds. For example, the initiation of a conference between a group of students could occur from the perspective of the dispatcher introduced in the previous slide every few seconds if the operator of the dispatcher is large, and much more frequently if the operator is Zoom or Microsoft. To conclude, a distributed system has several properties that identify them among all computer systems. But in this course, we also study larger distributed systems that go beyond this definition. Let's start with an example there. In our example, World of Warcraft, a modern and complex online game that started almost 20 years ago and still entertains millions of active players, operates a kind of vast, coordinated, super distributed system. World of Warcraft operates many shards, distinct worlds, where thousands of players can seamlessly interact with the virtual world in each of the shards. And each shard is serviced by a cluster of machines. And next to the virtual world, it must perform other classes of functions, for example, to persist the state of the virtual world and analyze it for various purposes. The clusters of machines are hosted in data centers spread judiciously around the world, close to players. In 2004, there were already 10 data centers with in total 13,250 server blades, totaling over 75,000 processing cores and 1.3 petabytes of storage. At this scale, World of Warcraft was comparable in size with the IT infrastructure of the largest scientific experiment known to humankind at the time, the CERN Large Hadron Collider. Both World of Warcraft's infrastructure and the World Large Hadron Collider grid although architected very differently, are similarly scaled and good examples of early distributed ecosystems. We will give a proper definition to these systems in Module 6. To understand the concept, we must also understand where the definition stops being correct. In other words, what is not that concept. Although the list of computer systems that are not distributed is long, two classes are prominent: single computer systems and parallel computing systems. The single computer system can be trivially understood. You are most likely accessing these lectures online from your single computer system, typically a laptop, a desktop, a tablet, or a smartphone. The case of parallel computing systems is more interesting. So let's explore it together by contrasting its features, summarized on the right of this slide, to those of distributed systems, summarized on the left. Simplifying, a distributed system is distinguished by its workload with multiple jobs, or single jobs but comprised of multiple, often many, tasks, with or without interdependencies between them. The users of the distributed system often focus on throughput, although some users do care about the speed up of particular or even single jobs. The main technique for scaling is horizontal scaling, adding more machines with different locations. The high latency of communication between components imposes that communication is kept infrequent. Execution is also synchronized at key points, but still kept infrequent. The hardware in use is often heterogeneous in nature. And multiple owners with mutual interests share or control their infrastructure together in a distributed system. In contrast to such systems, in a parallel computing system, the workload is often comprised of a single, massively parallel job. The main metric of interest is speed up for one job. The main technique for scaling is vertical scaling, adding more resources but inside the existing machines. In a parallel computing system, relatively low latency of communication allows that communication and functions depending on it, such as synchronization, to be frequent all the time. The communication characteristics further enable the simultaneous execution of various computational threads. The hardware in use has to be more restricted. It's often homogeneous in nature. In parallel computing systems, a single owner typically operates the entire machine, the big iron. But this theoretical distinction between parallel and distributed systems is becoming less prominent in practice. Modern real-world infrastructure is often both distributed and parallel.